Hello everyone, I hope all of you are doing great and you have started with coordination compound videos, right? And till date we have reached IUPAC nomenclature of coordination compounds. In the last class we have spoken about how to write down the IUPAC nomenclature from the structure that has been given, right? Suppose you have a formulaic structure of coordination compound and you have to write down the name. So now we know what is the sequence that we are supposed to follow, right? Today we will talk about some more rules so we are perfect with IUPAC nomenclature. So let's get started. So now let's understand the rules for all the ligands. We know very clearly that there are three types of ligands. You have neutral ligands, right? Then you have positive ligands or cationic ligands, and you have anionic ligands. That is the negatively charged ligands. We have done a separate video on that. If you want, I will attach the link for it. Okay, so now when you have the ligands, the name will be a bit different. Okay, so just pay attention to it. If you have a neutral ligand, they are usually written as molecule. There are some ligands which are not written as molecule, so I'll let you know. Okay, so neutral ligands which are written as molecule we are talking about right now. So it is pyridine. Okay, so if you have C5H5N, then it is pyridine. Okay, then you have this molecule, you can see CH2 is ethylene and you have NH2 on both the sides, so it is called as ethylene diamine. Okay, so in organic chemistry also you call it as ethylene diamine, and when you write down the IUPAC nomenclature for coordination compound, the name still remains the same. Okay, that is the reason we are saying that the name is written as a molecule. Okay, the next one, this is triphenylphosphine. Okay, usually in organic chemistry if you say it is called as triphenylphosphine, but even when you write down in coordination compound the name is written the same. Okay, but let's assume that you have water, H2O, so you does not write down it as water. This is our neutral molecule. Water is a neutral molecule, but in organic chemistry it is written as aqua. I repeat, it is written as aqua, and this is very frequently used. Okay, similarly you have one more thing, that is Nh3 Ammonia. Ammonia is also having a different name. It is called as amine. So for now, try to remember these two exceptions, that is they are neutral ligands, okay, but they are not written as molecules. These are the one which is most frequently used. That is the reason we are talking about this. Others I'll let you know. Okay, so I repeat, H2O, water, is called as aqua as a ligand. Nh3 ammonia is called as amine as a neutral ligand. Okay, the other one, positive ligand. So when you talk about the positive ligand, they have the ending IUM. So as soon as your IUM ending, you should know that this is the positive ligand. But of course, for becoming a ligand, it should have at least one pair of electron that it can donate. Okay, so remember that. So here if you see, hydrazine is NH2NH2. Okay, I repeat, hydrazine is NH2NH2. Okay, this pair of electron can still be donated. Okay, therefore it is a ligand. This pair cannot be donated, okay, because it is having a positive charge. So since it is having a positive charge, hydrazine becomes hydrazinium ion. Okay, NO plus, you can say it is nitrosonium. Okay, यहाँ पे what will happen in this case? The nitrogen will get donated. Okay, sorry about using my personal language. So when you talk about NO plus, again it is called as nitrosonium, or you can also call it as nitrosilium ion. Okay, fine. So oxygen is bearing the positive charge, but still nitrogen has a pair of electron which is getting donated. Therefore, it can behave as a ligand. So neutral and positive ligands have only some rules. Okay, let's talk about anionic ligand. The rule is simple, okay, but you have a lot of anionic ligands, so we need to remember more names. So let's have a look at that. So now let's talk about the anionic ligands. So in anionic ligands, we'll talk about three different types, okay, where we are replacing three different suffix with something else. So the first one is IDE with O. Okay, so the suffix IDE is been replaced by ending O. What I mean? Let's understand this with help of an example. Let's say you have Cl minus, okay, if we call this as chloride. So chloride ending is IDE. So now we will replace that IDE with O. So the chloride becomes chloro. Okay, and you can also write it as chlorido. So in some books you can also find this name. So you should not be confused what is happening. Okay, so I'll write down both the names. So chloride becomes either chloro or chlorido. Okay, similarly your bromide becomes bromo or bromido. So in all these cases we are replacing the suffix ide and it is now becoming o. So we are going to end it with o. Simple. Okay, the next one, cyanide becomes cyano or cyanido. Okay, then see, it is O with 2 minus charge. So this is oxo, or you can say it is oxido. If you have O2 with 2 minus charge, it is peroxide ion, right? So peroxide ion becomes peroxo or peroxido. Anything that you like, you can use it. Okay, the next one, OH minus is hydroxide, that becomes hydroxo or hydroxido. Hydroxo is more frequently used. H minus is hydride, that becomes hydrido. N3 minus is nitride, which becomes nitrido. O2H minus, the minus charge is on the oxygen, okay, it becomes perhydroxide, which is now nothing but perhydroxo. Okay, H2 minus is sulfide, that becomes sulfido. You have NH3 is amine. Okay, ammonia we are writing now as amine as a coordinate ligand name. But if from ammonia, if you remove one hydrogen, that becomes NH2 with a minus charge. So that NH2 with a minus charge is called amido. So your NH3 amine, okay, when one hydrogen removed, it is NH2 minus. That NH2 minus is nothing but amide. So ammonia with one hydrogen less is amide, and IDE replaced by O, that becomes amido. Amido with one hydrogen less, that is NH, it already had one minus charge. One more hydrogen removed, so you will have 2 minus charge. So that becomes NH2 minus. So when you remove one hydrogen from amide, that becomes imide, and IDE replaced by O, that becomes imido. So this is how you need to remember. NH3 ammonia, okay, NH2 minus amide becomes amido, okay, as a ligand name. Then one more hydrogen less, NH2 minus imide becomes imido. Okay, so this was when we were replacing IDE with O. Let's talk about the next one. Now, similarly like the first one where we have replaced IDE with O, here we are going to replace ITE, the last E, with O. That is, IT becomes ITO, or 8, ATE, 8 becomes ATO. Okay, so simply what we are going to do is remove the E and replace it with the suffix O. Okay, so these are few examples of that type. So your carbonate becomes carbonato. Okay, then you have oxalate becomes oxalato. SO4 minus sulfate becomes sulfato. NO3 minus becomes nitrate, becomes nitrato. SO2 O3 2 minus, that is thiosulfate, becomes thiosulfato. Okay, SO3 2 minus sulfite is sulfito. Then acetate is acetato. Now NO2, if you have, your nitrogen is going to have a pair of electron. Okay, if nitrogen is donating this pair, then you will say it is nitro, because the bonding of the metal, the central metal, is going to be with the nitrogen. Then you will use the name as nitro for the ligand. But if this oxygen is donating the pair of electron, okay, one of the oxygen O minus is donating the pair of electron, then you will say it is nitrito, because bonding is now via oxygen. So metal, the central metal and the oxygen will have the bonding. So this, just remember, this is important again because we use it very frequently. Okay, so that was all about the name of the ligands. So we now know how to write down the name of neutral, anionic and cationic ligands. Okay, let's talk about the last one, that is the bridge complexes. Writing down the name for bridge complexes can be most difficult initially, but it is very simple. Okay, so let's have a look at the rules. Okay, the first thing is always, whenever you are writing down an IUPAC nomenclature for any coordinate compounds, okay, or any coordination complexes, first calculate the oxidation number of the metal. Okay, now, so you can see very clearly the metal here is iron. So you have a square bracket. Inside you can see you have a complex. So your central metal is going to be iron. Here you have two same metals. In case you have two different metals, calculate the oxidation state for both of them. Okay, but now initially most of the time you will have the metal which is going to be the same. Okay, so don't worry much about it. Now, so for calculating the oxidation state, you can calculate as it is from this, or you can condense the formula. Okay, so let's see. Fe, how many Fe you have? You have 2 Fe. Okay, then you have OH minus and NH2, so NH2 and OH. Okay, and then you have water. How many water you have? 4 and 4, that is 8. Okay, the square bracket is closed now, and you have sulfate, which is 2. Okay, now calculate the oxidation state of the metal. So now you know that you have 2 Fe, and we want to calculate the oxidation state of Fe. NH2 is -1. Okay, then OH is -1. Water is neutral, so the charge of water will be 0. So even if it is 8, it does not matter. If you want to write down 8, just in case, you can write down. Okay, then you have sulfate. Sulfate has a charge of -2. Okay, and you have 2 sulfate, so 2 into -2. The overall charge, there's nothing, so you will write down this is equal to 0. Okay, the net charge of a molecule will be equal to 0. There is nothing over here, so the net charge you will consider as 0. Okay, just calculate for Fe. So you have 2 Fe. Okay, so -1 -1 -2, and then it is -4, that is -6. When it goes on the other side, that is going to be +6. So for Fe, each Fe will have a charge of +3. Okay, so once you know the oxidation state, writing down the name of this type of complexes becomes easy. Now let's understand what does the name means, bridge complexes. Okay, so if you have 2 or more metals, okay, which are sharing the ligands, okay, which are sharing the ligands, so this type of complexes are called as bridge complexes, and these ligands are called as bridged ligands. Okay, so here you have 2 bridged ligands, that is OH minus, and you have NH2 minus. Okay, so it is because of this, because they are forming a bridge between these 2 metal. NH2 is forming a bridge between these 2 metal. Okay, therefore it is called as a bridged ligand, and the complex is called as a bridge complex. Okay, so now let's start writing down the name. Now for writing down the name, always go from a sequence. That is, if you have a cation, write down the name of the cation. We don't have any cation, so we are not writing down that. After that, just come to this. Okay, that is your ligand. So now, which is the ligand that is attached to this? First is aqua. Okay, so how many aqua you have? You have 4 aqua. So the name becomes, I just want to write down a one continuous name, and that is the reason we'll just remove this. Okay, so you have 4 water, so you will say it is tetra, okay, aqua. Vowels, we usually write only once, A, E, I, O, U. If it is getting repeated, try to write it once. Okay, so it is tetra aqua. Then it is ion. Okay, what was the oxidation state of ion? +3, and you know that we are going to write it in Roman numbers, all the oxidation state in Roman numbers only. Okay, so tetra aqua ion, this part is done. Then you have the bridge ligands, follow the alphabetical order. Okay, so hydroxide, and you have amide. The ligand name becomes hydroxo and amido. So amido is starting with A, so you will write down amido. Okay, because it is the bridge ligands, you have to indicate it is different from this one, right? So for bridge ligands, we use the symbol mu. Okay, just remember, for bridge ligands, you will use this symbol, that is mu. Okay, for this and for NH2. So now we are going to write down amido. So mu, amido. Just write down mu properly. Okay, you will use hyphen on other side, because just indicate it as number. So numbers and the alphabets are separated by hyphen. Okay, so mu, amido. Next, again mu, hydroxo. Okay, so this part is done. Then again we are coming to this. So first ligand followed by the metal. Okay, so again you have 4 aqua. So tetra aqua. Okay, then you have ion with oxidation state 3. Okay, and then you have sulfate. That's it. The name of the complex is done. It looks complicated, but it is not if you follow the sequence. Okay, if you have noticed one thing, here there was 2 sulfate, but I have just written sulfate. Okay, I haven't written disulfate or something like that. So remember, in coordination complex, anything outside the square bracket is always treated as mono while writing down the name. So you have 2 sulfate, 3 sulfate, 4 sulfate, does not matter. You will just write down sulfate. Similarly, if you have a cation, let's say Na3, you will still write down only sodium. K4, only potassium. Okay, no tetra sodium, tetra potassium, nothing like that. Is this clear? So anything outside the square bracket, cation or anion, is written only once. It is not going to have a prefix of di, tri, tetra and so on. Okay, let's once again just have a look at the name. So we are going to follow the sequence. If there is a cation, then we will write down the name of the cation, but there's none, so forget it. Okay, then again start with the ligand always. Always the metal name will come after the ligand. Okay, so remember that. So tetra aqua ion, oxidation state was 3, mu amido, mu hydroxo, tetra aqua ion 3 sulfate. We have just followed the same sequence. Okay, so I'm giving you one more example to solve. So let's write down the name for this one. Again, calculate the oxidation state of the central metal. Okay, so now you have sodium. So sodium will have a charge of +1. You have 2 sodium. Okay, then ethylene diamine, it is neutral ligand. So how many ethylene diamine you have? 2 plus 2, you have 4. We are just taking it together. Okay, then we are going to calculate the charge for cobalt. You have 2 cobalt, so just write it as it is. Okay, NH2, you have 2, each of them has a charge of -1. Okay, then you have sulfate, 3 sulfate, each sulfate with a charge of -2, which is equal to 0. No charge over here. Okay, calculate the oxidation state of cobalt. So now you have, this is +2, then you have this -2, so that is gone, so that is 0. So 3 into -2, that is -6 again. So 2 cobalt is equal to, on the other side if it goes, it is going to be +6, right? So each cobalt will have a charge of +3. Is this clear? So oxidation state is clear, that the charge of this is +3, the charge of this cobalt is +3. Okay, let's start writing down the name of this complex. So now let's change the pen. This is sodium. Again, it is 2 or 3, does not matter. You just have to write down the name once. Okay, so sodium, right? Then after that, ethylene diamine is a chelate. Okay, so for chelate, that is, if you have a bidentate, tridentate, tetradentate ligand, you know that if it is getting repeated, you will use, if it is 2 times, you will use bis, 3 times tris. I have already taken the rule for that. Okay, so it is 2 times over here, so you will say it is bis ethylene diamine. En is ethylene diamine. Okay, sorry. So bis ethylene diamine, then cobalt, oxidation state of cobalt, that is 3. Both of them are same, so we can write them together. Okay, so again, because they are bridge, mu. Okay, because there are 2 times monodentate ligand, but so you will use diamido. Okay, so chelate you have used bis if it is 2 times. Okay, this you have used di, tri, tetra and so on. Fine, again come back to this. You have ethylene diamine. So again you will say 2 ethylene diamine. So bis ethylene, okay, I will continue here, ethylene diamine. Okay, cobalt, oxidation state of cobalt is 3, and then your sulfate. Okay, now some people feel that this is too big, so there's one more way that you can write down the name. So let's talk about that one. Okay, so this is one way, as similar as the first one. Okay, I'm showing you the second type, so you can also practice the name for the first one that we have solved. Okay, so let's write down the name. So this is sodium, this will remain as it is. Okay, you can see that the metal is same. You can write down this type of name, the second one that I'm saying, only when the name of, when the metal is same. Okay, fine. So because the metal is same, you can do it as sodium. Okay, So this is, and this is, just add them together. So 2 and 2, that is 4 ethylene diamine. So 4 will become tetrakis. So sodium tetrakis ethylene diamine. Okay, so all 4 came together. So tetrakis ethylene diamine. Okay, then you will write down the amide name. Okay, so then it is mu diamido. Okay, metal name at the end. So you have cobalt. Sorry, you have 2 cobalt, because here you are writing down the name 2 separate times. So you will just say cobalt. Here you are writing down together. So you have to say it is 2 cobalt. So dicobalt. Okay. After that, because you have dicobalt, okay, oxidation state will come only once, because both of them have the same oxidation state, that is 3, and then at the end sulfate. Is this clear? I repeat, you can write down this type of name usually when both the metals are same, okay, or sorry, if both the metal is different, or both the metal are same but they have different oxidation state, then you will follow this one. So this was much simpler. It looks big, but it was very simple. So I talk about this first. Okay, so whichever name you are more comfortable with, you can practice that one. But for MCQs, you should know all the types. That is the reason I have taken this. Okay, so I hope this is very clear to all of you. This was all for this class. Okay, in the next class we'll follow, we will practice more IUPAC nomenclature of coordination compound. See you soon in the next class. Thank you.